All right, good morning and happy Tuesday. It's May 16th, and I'm planning on doing the LeetCode contest from last Saturday. I think it's 3:45. So here we go. Contest 3:45 virtually, and it's time to shine. Open these guys up. Looks like two easies, two mediums. Okay. Clockwise order. Clockwise direction. 2K, 3K. Okay, IK. Okay. So we'll just wrap around, right? The game ends when you get the losers of the game are the friends who don't receive the ball in the entire game. So the game ends when you get the ball. One person gets the ball twice, right? Okay, that makes sense. Just mark scene and then go around in loops. All right, okay, so it is 5:55 in the AM. Game plan, loop around, use a set of scene. In K, scene is a new set. 4 and 5. So all the non-scene values. All right, so 1, 3. Your friend receives all for a second time. Hold on, let's go through this example real quick, just to make sure I solved the right problem. All right, so we have 1, 2, 3, 4, 5. The ball starts here. Then we go to the third friend, just 2 away. Then we go to the 1, 2, 3, 4. Go to this guy. Then 1, 2, 3, 4, 5, 6. Right. Okay. Step equals 1. Step, how about I is 0, or I is 1. Okay, so while I not in the scene.add I, that's the first one. And then I equals, let's see, step I. Step multiplied by 2. And then I equals I plus K times step modulus n plus 1. Return I for I in range 1 n plus 1 if I not in scene. Okay, something like that. It should be 4, 5, 2, 3, 4. Uh-oh, that is not right. Seem to add I 5 and 2. Oh, oops. Step is just incremented by 1. Oops, plus equals 1. 4, 5, 2, 3. This is not right. Oh yeah, it doesn't take into account the 0. So I want it to be 0 through n. Make life easier on myself, right? I plus 1 for that, right? Okay, because it is one base index. Well, I did get 2, 3, 4. It's for the second answer, but not the first. I plus step. Or k times step. Well, I guess we don't need step, right? So let's just do this. HI scene. K plus equals K. I plus K modulus N. It's not right. Every value seen besides 2 is what it's saying here, which is not correct in the clockwise direction. Oh, that's not right. Okay, so step is K. Okay, so step plus equals K. That looks right, right? Okay. That was good. Okay, cool. All right, 5:55 a.m. to 6:02. A little bit tricky, right? 7 minutes for implementation in Python 3, which is accepted. Yay. Okay. So I threw myself off a little bit, and then I started off with one base indexing, and then I had a couple of simple mistakes, but could be worse. Yeah, perform the simulation. I were they players? Call them players or people? My friends. Tracking scene values in a set and an unordered set for O of 1 lookups. Kotlin, JavaScript, Python 3, Rust, C++. right. This is Python 3. That one's cool, right? Step. And commit the step, okay. In K. Let's do this. Step 0. Set is owner set integer scene. Insert I second. So when we insert something into an unordered set in C++, it returns a pair. The first of the pair is an iterator to the element, whether if it exists or not. I guess like it'll be added into the set perhaps, or it might already be existing. The second of the pair is a Boolean value, which indicates whether it was inserted or not. So if it is successfully inserted, then it returns true. Right, so anyhow, let's do this. AI losers. I guess we call it losers, right? Right, so if it's not in scene, then we'll call these guys losers. Say +1. Step plus equals K. I equals I plus step modulus N. Looks good. That's cool. Actually, let me see if I can clean this up a little bit. If I can do generate, I'm thinking generate N from 0 to N inclusive, or N -1 inclusive, right? Output generate in, nah. Yeah, it's good enough. Okay, let's move on, whatever. C++ is meant to be written procedurally for the most part. It's hard to make it functional, especially functionally concise. Anyhow, let's do this. Scene is a new set. Zero scene step 0 while scene that has I. Scene that add I. Step plus equals K, and I equals I plus step, modulus N. Turn. Zero to N minus 1, filtered and not seen, right? Not seen that has I. That map to I plus 1 for 0 to 1 base index mapping. Looks good. Suppose for the Python solution, just stick this in one line too. All right, that's cool. Scene ith step. How about? That should be fine, right? The scene ith step. Scene ith step. Scene step. It looks good. Scene ith step. Set scene equals set I equals 0. And just make it consistent, right? It's cool. It doesn't really matter too much. But it's easier to read in the same order, than might as well just keep it consistent. All right, in K, copy. Scene ith step is a triple set of integers, 0 and 0. While not scene that contains I, scene to add I, step plus equals K, and I equals I plus step modulus n. Return 0 through n minus 1 inclusive dot filter scene that contains it map it plus 1 dot 2 int array. There we go. Looks good. That's cool. Okay, do rest, saving the best for last here. Let mute scene, mute I, mute step equals use SD collections hash set, hash set new values will be seen 0 and 0, and while not scene that contains, okay, scene that insert I step plus equals K, I equals I plus step modulus n. Then we'll return 0 through n non-inclusive dot into iter. Wait, I don't think we need that. Hold on. Dot filter ith value scene that contains. Okay. Dot map each ith value to I plus 1. Shorten this up a little bit. Collect it into a vector of integers. Oops. Okay. Let's see what happens here. Ooh. It's not that often I write the Rust and it actually compiles the first time, so that's pretty cool. Alrighty. So there we go, right? Perform the simulation of byte friends tracking scene values in order set for O of 1 lookups. Then return not seen values. I guess the one based index. Okay. Perform the simulation by friends tracking scene values in order set for open lookups, then return the one based index of not seen values I equals 0 to n minus 1 inclusive, right? Inclusive. Okay, so that's question 1, and it's done. We have 1 hour, 8 minutes left. Q2. All right, 1 hour, 8 minutes. Q2. Here we go. Okay, so it wraps around basically here. Zero, it's original 0, XORed with the one to the right of it. If it's 1, that means original sub 0 is 0, or original sub 1 is 1. There's no valid array. 0 and 1. I guess maybe we want to think inversion, right? Think inversion. Under what use cases is it invalid to create derived invalid, or I guess impossible? So example 3 is a case of that. And the array equals 1, 0. I plus 1. That's 0 and 1, which would be 1. And then this would be 1 as well. Or if we can just greedily perform simulation. See, this one's, and what if we do the XOR on the XOR? Right, what if we XOR it twice? Twice XOR to get original, maybe? Right? So, for example, 1, we XOR this guy, then it would be 1 and 1 is 0. 1 and 0 is 1. 0 and 1 is 1 as well. That's not right, though. Zero, 1, and then 1. It's 0, though. Next be this. 1, 1, 0. And X could be this. X is either 0, 1, 0 or 1, 0, 1. Either one would work, right? How to create that, though? Right, so just XOR it. Do the reverse. Create original via formula x of I. X of I, XOR x of I minus 1. And then wrap around the other way. Maybe that works. Example 2 is 1, 1. XOR these guys is 0. XOR 0. Yeah, that doesn't work. You run bitwise XOR. No, that doesn't work. Yeah, good idea though, right? Get the original from derived. Whenever there's a 0, we know there must be a 0 and a 1, right? We don't know the order of that 0 and 1. So either I or I plus 1 has to be 0 and the other one has to be 1. Almost like a 2-sat. I wonder if it's as simple as odd and even amount of ones. Here we see these are even amount of ones, and this is just an odd one. Could be that simple. I wonder, what if it's related to the count of ones, right? Odd or even. It would pass all the three use cases, I think, right? True, true, and false. That's worth a shot. Let's see what happens. Oh, okay. Well, that was kind of a lucky guess in that I saw that pattern. Yeah, it works. Otherwise, it's really too complicated, isn't it? Yeah, all right, well, whatever, I'll take it. Okay, so let's just squish this up real quick and then we'll move on. That was somewhat of a lucky guess. It's not like I did a proof or anything. Not sum of A and 1, right? So if there is an even amount or an odd amount, lambda, right? So if there's an odd amount of ones, then it's false, right? It must be false, right? So this is correct, right? Yes. It's impossible to create derived when there exists an odd amount of ones in derived. And this info was derived from deductive reasoning of example 1, 2, and 3. Right. Okay. So anyhow, yeah, that was cool. Few solutions. Return true if, oops, and only if the quantity of value 1 in the derived array A is even. It is impossible to create derived, like the derived array. Right here, use inversion to return true if, yes, use inversion. It is impossible to create the derived array and odd. Yeah, that looks good, right? Use inversion. Now you return true if and only if the quantity of ones. T of 1. Okay, right. So use inversion. my first intuition was correct, right? Under what use cases is it impossible to create the derived array? Okay, so grab Python. Let's do JavaScript next. All right, here we go. Usually dash some. It's even. Okay, I do Kotlin. Turn this into a Lambda. Might as well, right? If, no, we'll just return it, right? Yeah, some modulus 2 is equal to 0. Right, so it's even. Okay, that's cool. Do rest in C++ and then move on. Emulate a so if it's not odd, then it's even. All right, do rest and then move on here. A dot sum I32 is 20. Should be fine, right? Oh, oops. A dot into iter. Okay, that looks good. That's cool. Okay, let's move on. All right, a few solutions use inversions. That is, we return true if and only if the quantity of the value 1 and the derived value a is even. Since okay, that looks good. It's Q2 and we're on to Q3 with 51 minutes left. Q3. I'm gonna take a break and go grab some coffee too. 51 minutes left. Q3. Okie dokie. And for Q3, here we go. Ready? Okay, it has to be strictly bigger. Return the maximum moves you can perform. Start at 0, 0, 0, 1. Go diagonal. Go up and to the right, right, or down and to the right. Oh, okay, so we're always going to the right. Interesting. Okay. So this one we should be able to track the best using depth first search, right? And then memoization. I think that would work, right? Let's see, 1,000 by 1,000. Yeah, that should work. So yeah, this one's DP, right? We'll do top down. Let's memos the game plan. Array of M and N rows. Oops. Is M for J in range N. Best will be our maximum. Candidate is go IJ. Scene set. Best equals the maximum of itself and the candidate. And return best at the end here. Oops. Okay. Oh, I need to keep track of what time it is. It is 6:35 in the AM. Time to keep on shining. Okay, so if let's do the key. Key is IJ formatted as a string of what's actually no. We'll just use tuples, right? IJ in scene, or we need to keep track of our last as well. So we can only go to bigger values than our previous value. Last is mark it as 0 since value 1 through 1,000,000, or I guess it's out of bounds if I is less than 0, or j is less than 0, or I is equal to m, or j is equal to n, or ij in scene, or a sub I sub j is less than or equal to last, then we'll return 0. Otherwise, we return the maximum of going up and to the right, or down and to the right, right? The value plus that. Best equals a sub I sub j. So this is a local best, not a global best. Not to be confused with this best. This best is a little bit different than this best. Trying best locally. All right, so if we're on top of vest, we'll do UV as adjacent values. We can only go to the right. Candidate equals just do this a sub I sub j plus the best candidate. Maximum of itself and the best candidate, and then we'll do memoization so don't solve the same problem over and over. 30. Oh, that's not right. Oh, maximum number of moves. Okay, so maximum number of moves is 1. minus 0. So candidate is 1 plus best. Okay, so 3 moves is the maximum. Oh, that's 4. Okay, so we don't want to. It's best minus 1 because we do include the current step, right? 0 for that guy. Okay. 3. Uh-oh. 1 is not correct. Oh, do we have to start on the leftmost column? Ah, okay, so here we go. So that's the difference. I had a bug here. We have to use the leftmost column to start. So J is 0. Looks good. Oh, I need to add a memo. Okay, so this should TLE. TLE, right? And then we'll add a memo. And it should be accepted. Okay, yes. Big one. Okay, and then add our memo. Just super simple to do in Python, so we don't solve the same problems over and over. Unhash. Oh crap. Okay. Scene. Okay, so I don't want scene then. Oh, I'm not even using scene anyhow. That's funny. I didn't use scene. Okay. IJ and last. Unhashable. Okay, I don't want that anyhow. IJ last. Okay. Looks good. All right. Okay, so that's top down with the memo, which is accepted. And that was accepted at 6:41 in the AM. About 6 minutes for implementation in Python 3. Which is accepted. Yay. But +1 bug. Oops. Since I didn't add a memo initially. Okay, cool. So that's that. And then we can do bottom up, right? So 6:41 AM. It's bottom up time. Okay. So as the recursive stack unwinds, we'll go from the right to the left and then come back to the first. Or no, we can't go from the right to the left. We still have to go from left to right. Otherwise, it's invalid. We could have a path that ends at not the beginning. Okay, so we have our DP matrix, and then we'll return the maximum of the DP matrix -1. Right, so DP is 0 for in range. Oops. Right, so those are our columns. Wait, hold on. Oops, hold on. 0 times in columns 4 underscore in range m rows in columns. Turn the maximum -1 maximum of the row for a row in DP. Okay, and then try to copy and paste some of this stuff so others can see the correlation between top down and bottom up. So p sub I sub 0. So we want to go consider that guy. And then, okay, so the maximum is not going to actually exist there. This is going to be a little bit different because I can't follow the recursive stack unwinding explicitly since we might not get there fully. Like when the recursive stack unwinds, we might end up at a non-leftmost column. Well, I could just consider leftmost column maximum then, right? Maximum row sub 0. Yeah, so okay. Let's try to follow the recursive stack unwinding because that is the most simple case, right? So we'll only consider the values that are valid as the ones that have gotten back to the leftmost column. Okay, so then so we'll start at the rightmost column and go backwards. For I in range M, or J in range, reversed range, right? And backwards. And then we can add one for each one that's strictly less than. Right, so we want to grab this stuff. Yay. Now I want the jth column, one column at a time, backwards from left to right. So the best for each ith value be stored in dp sub I sub j. Okay, so we want this to be a little bit different. We want it to be the opposite, right? So we want if 0 is less than or equal to I less than M, and 0 is less than or equal to J is less than N, that is I and J are in bounds. Actually, U and V are in bounds, and A sub U sub V is strictly less than A sub I sub J. So we came from IJ, we're at UV going left, right? So we're doing top down, we're going recursively to the right. Bottom up, we're going to the left, right? So IJs are previous, which is last. UV is our current. Okay, so last I don't need to explicitly keep track of, but it would be dp sub u sub v. No, ij is our last one that we're at, right? We were at ij. I'm confusing myself. Ij is over here, uv is over here. Build up the subproblems on top of themselves as the recursive stack unwinds. uv is built upon ij. Okay, I think that works. All right, let's see what happens. No, that's not correct. Okay, so it's not quite getting there. So you don't want to wrap around all the way. A should be 1. Base case is 0. Therefore, overriding our values are first. Oh, oops, reverse range. In down to 1. Okay, that's not quite right. UV is less than IJ. What am I doing wrong here? This is 0. Candidate for best. Let's print out DP then for a small example. For row in DP, row. It's not palm at a time. V, I suppose we don't have to check. Maybe we do. Since we end at 1, V at most could be -1. It's the maximum of itself and the best for this guy. No. This should be UV, right? I'm getting myself confused. UV. Wait. UV. The G is over here. UV is over there. So I need to update this here. And then let's just do this, right? Instead of having these intermediate values, which are confusing me, right? So this guy can be updated multiple times based on that guy, right? So we want it to be the maximum. Okay, I think that works. 2. And since it's initialized to 0 instead of 1, we don't need to subtract 1, right? Okay, I think that works. Okay, and then can I get, let's just try it. Let's see what happens. Yes, okay, cool. That is anecdotal evidence that skill set with dynamic programming is improving. 11 minutes for bottom up implementation, which is accepted. Yay. And that can be a little bit tricky because we need to explicitly mention the base cases to be iteratively built upon, and we have to understand how the recursive stack aligns. Okay, so yeah, there you go. There's the art of dynamic programming. That's totally sweet, right? Okay, we got 30 minutes left, and I want to do this in the other languages, and I'll probably save the last question for later. Even though it's a 5, I could probably jam on it, but I'd rather finish this. Okay, so the art of dynamic programming, which hopefully is helpful for some folks. It's been helpful for me so far, and I'm still learning. Okay. Art to dynamic programming. Hopefully it's beneficial. And I would have loved to have had an article like this to read when I was first starting dynamic programming, because it's tricky, and most folks will try to show off and post their most concise bottom-up solution rather than saying, okay, this is how it's derived. Actually, the current column is only dependent upon the previous column, so we should be able to do memory optimization, right? One column at a time. Memory optimization, right? Instead of memoizing the entire matrix, we only need one column. I guess well, two columns prior to previous. So we can go from O of n squared memory to O of log n, right? From quadratic to linear. So call this guy previous 0 times m. So this is a previous column. This is our current column. This guy previous. And I suppose, yeah, we can clean this up a little bit. We don't need to do it this way. We can actually do it functionally. Let's do that real quick. Might as well clean these guys up. So I don't need best, right? Turn the maximum, go I0. I guess J, we could just say 0 as well, just to simplify this. Or I in range, oops, M -1. Should be cool, right? Got the memo in there. Yeah, that's pretty sharp, I think. So without the memo, the memo would look like this. Okay, and then bottom up, we can just return the maximum of this guy, the initialized state for I in range M. A little bit more concise, right? Less code, the merrier, I'd say, for the most part. Okay, and then the memory optimization is next. Memory optimized. So this guy is current. Let's see, so we need the column to be this guy. This guy will be current. Current U is built upon the previous I, right? Current U throw is built upon the previous I throw. J is over here, V is right here. And J and B are adjacent. As long as U is in there, and that holds. Okay, so that's cool. Previous equals current as we iterate from right to left columns, and then we'll return the maximum previous I in range. And right, so that should work. Yep. Big money, no whammies. Okay, cool. So there's our memory optimization, and we're done in Python 3. Actually, let me grab this real quick. Oops. Memory optimization. O squared to O of n. It's current on n's previous column. Derive current column from previous column. When solutions. Oops. Okay, copy and paste this into JavaScript solutions. Python 3 solutions. Done. We'll do REST solutions, and then we'll just skip these parts to do how to capture outer scope in recursive closure. I don't know. Closure. For REST, yeah, we'll just do the bottom up. And then do C++. Oops. C++. And then we can do these C++ as well. Okay, so copy and paste these guys, and then try to harden my knowledge of dynamic programming from basically just doing this over and over again, just pounding it in here. So I did do this in a decent amount of time, so that's pretty exciting, I think. It's improvement. Okay, so top down. Bottom up. The memory optimization is pretty cool, I think. All right, and we have 21 minutes left, so I'm gonna keep jamming on Q3, just really hit that hard so I can hopefully formulate solutions to DP problems faster during a real contest, where I think there's a little bit more pressure since my contest rating could be adversely affected. And then our dimensions of our matrix A. Fun equals function. Turn feature as the recursive section lines. Take ij and last. Go captures itself in its own lambda, so it can be invoked recursively. And do want a best down here. Turn the best at the end here, and then we'll just go through all of them. Start from each of these, and then candidate. Let's go I 0. That's right. Best is maximum best candidate. Okay, so if I is less than 0 or j is less than 0, or I is equal to m, or j is equal to n, or sub I sub j. Oops. Want it to exceed last. So if it's less than or equal to last, return 0. Either out of bounds or invalid move. Best is 0. Best here, and then we want to count the very last one. V in pairs of pair. Sure, we destructure this guy. Vector of pair. Of to the right, and then below and to the right. Candidate is go UV, and IJ is the last. Best is the maximum of itself, the candidate. And then I'll have to add a memo so it doesn't TLA. Oh, it's not right. Oh, 1 plus. Right, so that's a move. Come on, LeetCode. Gotta pay the big bucks if you want that action. Okay, cool. So that should be top down, add a memo. Oops. So we'll create a map. Map M, we're our memo. I'll need a key. I, J, and last will be our state that we're memoizing. Oops. Okay. J. And last. Okay. Base case, we don't need to memorize. Oops. K is our key. IJ and last. If memo does not have that, oops. Right, if we don't have it, then we'll compute the answer once and then store it in the memo for lookups, future lookups. Right, so you don't have to solve the same problem, overlapping subproblem more than once. Uh-oh. Stack buffer overflow. Really? Stack buffer overflow. This isn't even a big input. The heck did I do wrong here? Uh-oh. Last. I choose less than last. UVIJ. Oops. M. Okay, so that will do it. Oh, come on. Yeah. Oops. All right, simple mistake, but that will cost you +1 bug for that. Okay, so that's that. Now it's time for bottom up. Okay, so for each jth column from right to left. Ninth column, it doesn't matter which order we go, so might as well just do monotonically increasing. Oops, size less than M. They basically want to do the same logic, but then use the DP memo for the minimized state. So I'll just copy and paste so I can show y'all like how this is done, right? So this will be DP sub I sub J sub last, or actually last we don't need, right? So we'll use on our own here to minimize that state. Okay, so best here. It's need to populate DP sub ij based on this guy here. Guy will be DP sub u sub v for that state. I don't need to minimize last here. Actually, we just want to store it in UV, right? We don't want the intermediate state. So this is how we're using best in candidate will be 1 plus the previous, which is ij. Ij is over here, UV is over there. All right, so as long as UV is in bounds, if 0 is less than equal to u, u is less than m, and 0 is less than equal to v, and v is less than n, and a sub u sub v is strictly less than a sub I sub j, then it's valid, right? And something like that, right? Oh, map I don't need. Right, since I have the DP matrix. Oh, I need to define DP. And yeah, so DP, BVI DP, M rows in columns. Oh, 0 for all of those. Not quite right. We said I sub 0. Oh wait, hold on. J goes down to 1. Oh, and this needs to be J minus 1, right? So we're building the UV on the left and the IJ to the right. Okay, that looks good. A little confusion, but improved since my first iteration. And then we'll do memory optimization. Previous. Previous equals current. Current. This guy here. Previous. Oh, no. Current U is built upon the previous. Okay. This guy. Previous. Okay. There's our memory optimization. We don't need the entire DP matrix, right? We only need the rightmost columns, and that's cool. And I think I'm going to take a break. Let's see, how much time do we have? We've got 11 minutes. Yeah, I'm going to stop a little bit ahead of time and then do the other solutions here and a little bit offline. Right, so I'll basically do the same thing and pound the DP into my head so I can get a little bit faster each time, hopefully. And what's strange about DP is that there's a paradox in that if you see the solution, it's like, well, oh yeah, duh. But deriving the solution upon demand is quite a bit more difficult than simply looking at a solution and validating it in hindsight, right? So it's a skill set that has to be practically acquired. You can't just passively listen to lectures or look at other people's solutions, right? You need to use the practice using the right side of the brain for holistic, like more of a feeling, kind of like art, which is what I put here. right? It's not just the left side of the brain. It's not just a formula. It's a feeling. Okay, and yeah, there's the C++ solutions. So top down with the memos accepted, bottom up. It's kind of weird, but you can see what's going on with building UV from IJ, the current UV from previous IJ. Here we explicitly see the previous columns. Okay, yeah, so 9 minutes left. So, well, yeah, I guess I might as well jam on JavaScript or Kotlin just for a few minutes. Cardinality of the rows and the columns correspondingly. Let go. H0, last is 0. Turn race of m keys for each ith value. I to go I. Take the maximum of that. Spread out. Okay, so if I is less than 0, or j is less than 0, I is equal to m, or j is equal to n, or a sub I sub j is less than or equal to last, return 0. Best equals 0, return the best in here, maximum uv of I above right, down and to the right. Candidate is go uv, last will be ij. Best is the maximum itself and the candidate, something like that, right? And then, oh, that's not right. Subtract 1 there, and we need to add 1 here. These are our steps we're taking. That was good. We'll add a memo. It should be accepted. M is a new map. Key equals ij last. Oops. Ij last. Okay. That K is the key, ij last. Memo. If the map does not have that key, then we'll compute it once and then save it for future lookups. And get that key. Okay, so this should be accepted. Big money, no whammies. Okay, cool. Do it bottom up. How much time do we got? I got 6 minutes. Okay, bottom up time. Okay, and then we're going to turn dp I 0. dp equals two-dimensional array m rows by in columns. Build initially base case 0 minus 1 down to 1. So I don't need this. And I equals 0. It doesn't matter which direction we go for I. If hold on. That UV of, let's just grab this guy. See, this will be our main chunk. So the 1 plus our state is dp sub u sub v. then we're going to say DP. So, oh, wait, oops. Previous is IJ. Current is UV. Maximum of itself. Oops. And 1 plus the previous state. If 0 is less than or equal to U, right? U is in bounds. M, 0 is less than or equal to V, V is less than N, and A sub U sub V is strictly less than A sub I sub J. Okay, something like that. That is not correct. We don't need to subtract 1 here. Really, it's all zeros? It's not getting to the base case correctly then. J is n minus 1. Oops, yeah, so this one, yeah, we're going from the right to the left, so I need to build it this way. Okay, that looks good. That's cool. We got 3 minutes left, so might as well do the memory optimization, and then I'll go out to the bus with my kids and call it a day here. Previous equals array m build with 0. Current will be here. Current equals array m, right? So that's the previous and current column. Previous equals current for each iteration. And then current u is built upon the previous I, right? And then we'll just use previous here. Okay, that should be good. And yes, we're good to go. Okay, so 2 minutes left. I'm gonna take a screenshot of this guy. Oops, okay, here we go. Post this on YouTube. Hopefully it's helpful. I would have loved to have had something like this when I was first starting DP, because DP is tricky. It's not necessarily straightforward, I don't think. Okay. So anyhow, post this here. There. Down. Memory optimization. Oh, oops, actually I don't need the map and the key for this guy or that guy. So let's clean this up a little bit. That should be fine just like that. And the map and the key are only used for the top-down solutions. I have explicit memo bottom up, so that's cool. Okay, and then the memory optimization. Okay, cool. So I'll post this, and then I'll do Kotlin and all that, Kotlin and Rust here later on. There's 33 seconds left, so might as well just grab one more screenshot. It'll be the most up to date. 30 seconds left. Overwrite it. So I'll do Kotlin here in a little bit, but this is it. Well, she wrote. Pretty decent solutions, I think. So I'm gonna go. Okay. Yeah, we'll catch you all later.